Imagine you're walking down the sidewalk. It's a beautiful day when you remember it's your grandmother's birthday. You reach into your pocket and pull out your phone. But when you look at your screen, you see a timer on it. 3, 2, 1. Suddenly your phone starts to get very hot. You drop it on the ground where it bursts into flames. Now the scenario may sound like a hyperbole, but to owners of the Samsung Galaxy S7, this experience is all too real. Recently, owners of the S7 have been experiencing issues where their phones catch on fire. Now what's happening here? How is it that an ordinary device like a cell phone is turning into a ticking time bomb ready to burst into flames? Well, the issue lies in the battery. In this case, the lithium-ion battery, which has been the focus of my research here and was what I want to talk to you about today. Now, lithium-ion batteries are great. They have a very high energy density. This means that for a small amount of lithium, you get a lot of energy. You can think of it like comparing the amount of caffeine in a cup of coffee versus that in a 5-hour energy shot. While the 5-hour energy shot may be a fraction of the size of a cup of coffee, it can have equal to or more caffeine. Similarly, lithium-ion batteries have a tremendous amount of energy in them, especially when compared to other battery systems. But like any cutting-edge technology, there's a lot that we don't understand with lithium-ion batteries, and this leads to problems. One of these problems occurs during charging. When you charge a lithium-ion battery, you take the fuel, or lithium, and move it from the positive electrode to the negative electrode. This electrochemical process is rather complicated, but it can be likened to the filling of a parking deck on a busy day. At the beginning of the day, the deck is empty and ready to be filled, and so cars can come in. But as the day goes on, the deck fills up and traffic can back up down the street, leading to problems. Similarly, when you charge a lithium-ion battery, lithium may not go into the electrode and can build up on the surface, forming things called dendrites. Now, these icicle-like dendrites can grow from the negative electrode and go all the way back to the positive electrode, creating an undesired internal short circuit. This short circuit can lead to an excess of heating, leading ultimately to the battery catching on fire. Now, my research has focused on developing a technique to study the growth of these icicle-like dendrites. And the novelty and the beauty of my technique is that it's non-destructive. Typically, when you want to find out what's going on inside a battery, you have to open it up. Now, inherently, this destroys the battery and prevents you from doing further testing and further analysis. But my technique utilizes in a new way some fundamental principles like current, voltage, and resistance, and allows you to watch these dendrites grow inside the battery without opening it up and destroying it. That way, manufacturers like Samsung can use this technique and eliminate their flaming battery problem. That way, the next time you go to call your grandma, you pull out your phone, you won't see a timer counting down on the screen. Rather, you can swipe right, make your call, wish her a happy birthday, and then continue on and probably make her day. This is all made possible by research here at Texas A&M University. Thank you very much for your time.